Hello, so let us solve the problem now. So we are supposed to calculate this double integral on the parallelogram region with these corners. So I have sketched that domain here. So these points that you see are these points with these coordinates, and this is the parallelogram. So this D is every point on these edges and including the interior points of this parallelogram. So that is the region D. And I want to integrate this over that region. And it is mentioned in the problem itself that use the method of substitution of variables to solve the problem. But my point is that even if it is not mentioned there, yes, it is a good idea when you have a quadrilateral domain, and if it is not mentioned in the problem, use the method of substitution. Try to understand your domain as usual by finding the equations of these lines. Okay, so let us, for example, do it here on the board. Yes. So, for example, for this one, the coordinates that I have here, this is 1 and 1. And the coordinate that I have here is actually 0 and -1. So if I want to find the equation for that, an equation for that line, I calculate the k value. So the k value is the difference between the y coordinates. So let me write 1 minus -1, which is 2, and 1 minus 0, which is 1. So this is exactly 2. And then I can find the equation. So I would say y minus, say, let me use this one, y minus y node, which was positive 1, is equal to the k value 2 times x minus 0, which is just simply x. Okay, and then what I do, I get, usually you put y alone and move 1 to the other side, but don't do that in this problem, because in problem you see that 2x minus 1 appears in your integrand, and usually this is the case. This is helpful when the equation of these lines have something to do with the integrand of your function. So this motivates me to move y to the other side. So this gives me 2x minus y is equal to 1. Yes? So this is one equation. So if I ask you what is that one, so you can continue this line. So let me write them. So if I continue this line, the equation of that line is 2x minus 1 minus y equals to 1. And of course, this is the same line, so it has the same k value. So the equation of that line would also be 2x minus y equals to a constant, so let me call it m, because this line is parallel to that line. It's a parallelogram, and it means that, okay, to find m, I can choose one of these points and put it here to find m. Or either, if you want, you can just use these points to find the equation for the line. It doesn't matter here. So this point has coordinates 2 and y 0. So if I, instead of x I put 2, instead of y I put 0, so it becomes 4 minus 0 is equal to m, so m is 4. Yes? So I can clean that, and I write this one is my equation. Yes? So what I can do, so I can write that equation for this line is 2x minus y equals to 4. Okay, I will do the same thing for one of these lines. For example, let us take that one. So what is the slope of that line? So this point has coordinates 2 and 0, and then this point has coordinates 1 and 1. So if I ask you what the k value is, you subtract them, it becomes 1. You subtract them, it becomes -1. So the k value is -1. And then, for example, I use this point to write an equation. So it becomes y minus y node, which is 0 k value times x minus 2. And then what happens? Y becomes 2 minus x. Usually this is the standard way that you write, but again, as I told you, by looking at your integrand, you realize it is a good idea if I move x to the other side, yes? So this gives me that x plus y is equal to 2. So that is the equation of this line. So this is x plus y equals to 2. And then, for example, the other one, because parallel to that one, so again, you can use the same trick. You can say it is x plus y equals to m, and then you know that this point should satisfy on that one, but this is 0 and minus 1. So m becomes minus 1, simply. Yes. So this is what I have, and this is actually your domain. So everything you see here and on the rim of this quadrilateral is your domain, and you are supposed to integrate on that. So by the way, if you want to integrate this directly, then you have a little bit of hard problem. So you have to divide this domain into two parts, and then if you want to give the role of your free variable to x, then you have to move x from here to this border line, and then do it once more from here to there, because when you are on the left hand side, the y value goes between these two lines, and immediately after that line, the y value goes between these two lines. This is one problem. Another problem is that you also need to work a little bit harder to integrate this. So it is possible, but using the substitution method will solve the problem easier, especially when you see that the equation of these lines have something to do exactly with the integrand. So this motivates you probably to say that let, for example, 2x minus y, let u be 2x minus y, and v be equal to x plus y. Okay? Then what happens? The integrand that you have is x plus y over square root of 2x minus y. It turns into a new function of new variables, yes? So this becomes the function. Instead of x plus y, you can put v, and instead of 2x minus y, I can put u, so this becomes square root of u. So let me just tell you, if you want to name this function is f of x and y, for example, to x plus y over square root of 2x minus y. By this substitution, I changed my function to totally new function because the functional form is different. You see, I want you to feel that you have to change the name of the function. Because if I ask you what is the role of this function f, you will tell me that this f takes an ordered pair from you, add the numbers, and put it in the numerator. But this function is not doing that, you see. This function is taking an ordered pair from you and picking up the second component and put it in the numerator. So the function is really changed, so you're not allowed to use the same name for your function, the same name as I did before. In the denominator, it takes you an ordered pair and then multiply the first component by 2 and subtract the second component from it, take a square root of it and put it in the denominator. But this function is completely doing different thing, yes? This function, only for the denominator, it only cares about the first component and take the square root of that first component and put it in the denominator. So these two functions are really doing different things. So they deserve different names in mathematics. Okay, this is one thing. Another thing is that we need to know how dA is changed after this substitution. And hopefully you have studied, you know that it has something to do with the Jacobian, yes, of this coordinate transformation. So I would say that dA, which I can write dx dy, goes to not just simply du dv, unless under very special circumstances, but it goes to du dv multiplied by a positive number, the absolute value of the Jacobian of the old variables x and y with respect to the new variables u and v. Okay? And what the Jacobian is, it is defined in that way, that the Jacobian of x and y with respect to the variables u and v is defined to be a 2 by 2 determinant. The first component, you take the partial derivative of x with respect to the first new variable you introduced, and you do the same thing with respect to the second new variable you introduced, and you do the same thing for the y variable in the second row. So this is just the definition of the Jacobian. Of course, y, this is supposed to be like this, you have to go and study the book, see the proofs. Okay, but I'm just using it. Okay, but one thing that I want to mention here, these two parallel lines shouldn't be confused with this determinant sign. So determinant is a number. It could be positive or negative or even 0. And then whatever you get here, you have to take absolute value from the result. Okay, don't get confused between these parallel lines. Okay, but then you see that you usually you are in trouble a little bit. Why is that? Because here, if I ask you calculate partial derivative of x with respect to u, you expect to have x as a function of u and v. Okay, so you need to know how x is expressed in terms of u and v if you want to do the partial differentiation. But the equations that we have introduced expresses u and v in terms of x and y. So you have two alternatives here. Either you solve this, you set up a system like this. You say that, okay, let me pretend that u and v are given and x and y are unknown, and I solve a very simple system of equations and express x and y in terms of u and v, and then I can directly use that. This is one alternative, but usually solving equations might be hard, especially in the case that these are not linear equations. Okay, so this is why it is better to use a theorem, which is a consequence of the implicit function theorem. And it actually tells you that instead of doing this calculation, you can calculate the Jacobian of new variables with respect to the old ones, exactly defined in the same way, meaning that I take the partial derivative of u with respect to x, partial derivative of u with respect to y, partial derivative of v with respect to x, and the same for y. Okay, and I calculate this. But if you want to calculate the one that you need to remember you have to find the reciprocal of that number. Okay, why this is easier to calculate in our case, usually when you do the substitution method, this is easier to calculate because you introduce new variables in terms of old variables. Okay, but what you need is always the Jacobian of old variables with respect to the new variables. Okay, so this means that the partial derivative of u with respect to x. So I go to u. This u is a function, is a function of two variables x and y. I want to partial differentiate it. I am giving the role of my variable to x. It means that y is considered to be constant. So if I differentiate with respect to x, this becomes 2, this becomes 0. So the first entry of this determinant is 2. And if I do the same thing with respect to y, I get -1. And now I go to v, partial derivative of v respect to x is 1. The same is true for partial derivative of v respect to y. And then you calculate this determinant. 2 times 1 is 2, minus this times that 1. So finally the answer becomes positive 3. But again, this is the Jacobian of the new variables in terms of the old variables. So this means that what I need is the absolute value of that. So let me just write it simply like this. So let me write it like that. So I can now answer this question, yes? So I can write here that dx dy in this transformation goes to absolute value of the reciprocal of that number multiplied by du dv, but of course this is simply a third du dv. Okay? So this means that the question mark, the integral here, is equal to the double integral of my new integrand, yes, multiplied by this combination. So if you don't mind, let me pull 1/3 out, and then I have du dv. But not in the old region, because the region also changed. Yes, this is the reason that I already drew another one. So let me call this one, for example, I don't know, let me call it E. What is E here? E is the transformation of this quadrilateral in this coordinate transformation going from XY plane to here, which I call it UV plane. Okay, so how does this change? It is simple because the transformation is extremely simple here. You see, 2x minus y, if you see, I called it u. So here, if I ask you, how can I write this line? How can I represent this line? This line is the line that 2x minus y is 1. But 2x minus 1, I gave it a name u. So if 2x minus y is 1 in xy plane, it is transformed to the line u equals to 1 in the uv plane. Yes, so this becomes, for example, u equals to 1, and then this means that this will actually change to this vertical line, which is u equals to 1. So this means that under this coordinate transformation, this line is being projected onto this line. Yes, not the edge. The whole line is transformed to u equals to 1 because this is nothing except 1. And if I ask you the same question about this, you immediately answer because this is u and it is 4. So this means that every point here with coordinates x and y satisfying this equation will be transformed to a point there so that the u component of that is 4. So it means that, okay, this is 1, 2, 3, and 4. So this is another line. Yes? So this is u equals to 4. So, and then I can do the same thing for v. If I ask you what this is, you will tell me that all the points on this line satisfy this equation, but x plus y is defined to be v. So it is v minus 1. And this one is v equals to 2. So v is equal to minus 1, somewhere here, and v equals to 2. So, but you know that v equals to something is a horizontal line. If I choose to take this coordinate, the vertical axis to be v, of course it doesn't matter if you change them, it doesn't affect the result. Okay, so this is v equals to 2, and this is also v equals to 1. So now, this domain D is actually mapped onto, in a one-to-one way, mapped to this region. That is what I called E there. And that is actually the core idea of substitution. You see, this is not a standard. You know that in calculating double integrals, the simplest possible regions are rectangular regions for which the sides are parallel to the coordinate axes. Okay, here I have a quadrilateral, but of course the sides are not parallel to my axis. So the whole point of this transformation made life simpler for me. Instead of calculating this integral on this region, which is more complicated, I need to calculate this new integral on a new domain, but calculating this on this new domain is extremely simple because my region is rectangular on the first place, and then the sides are parallel to the coordinate axis. Okay, then it doesn't matter which one you want to take the free variable, because for rectangular regions of this form, it doesn't matter that much. For example, let me choose u to be my free variable. So what do I mean by that? So I put 1/3 here, and what I do, I decided to take u as my free variable, so I put it outside, and then I have my integrand, another integral. I have v over square root of u, and then I have dv here. Okay, if I ask you what are the limits for du, you will tell me that, okay, now because I am working in this region, u starts from here, okay? This is the smallest possible value of u anywhere in this region, and this is the highest value of u anywhere in this region. So it goes from 1 to 4. Yes, so it goes from 1 to 4. But this is again important. It doesn't matter which one I am choosing. Any u that you choose anywhere here, the v coordinate independent of your choice, this is important, independent of the choice you make for u goes from 1 to, is it 1? No, sorry, this is minus 1. X plus y is minus 1 here. Okay, so it goes from minus 1 to 2. It is important. For any choice of u that I make, v independent of that choice for u, for my free variable, goes from this limit to that limit, which is from minus 1 to 2. Okay, so this means that it goes from minus 1 to 2. And then I have to calculate this integral. So to calculate this integral, what I do, I will first calculate this inner integral. Okay, but this integration is with respect to v, so square root of u is a constant, so I can pull it out and just concentrate on that one. So if you don't mind, let me call this integral I, but because I am integrating over v, it will be a function of u. Okay, so let me calculate I of u here. Okay, so what is I of u? I of u is equal to 1 over square root of u is a constant for this integral, so I pull it out. And then I have integral from minus 1 to 2, and then I have v dv. But this is extremely simple. A primitive function for v, when v itself is the variable, is v squared over 2, but I have to run it from minus 1 to 2. And if I do that, 4 divided by 2, 2, and then minus a half, so it becomes 3 halves. So it becomes 3 over 2 square root of u. This is just IU. But after the IU is calculated, I have to calculate 1/3 of this integral with respect to u from 1 to 4. So finally, my question mark is equal to, I have a 1/3 there. I also got a 3 over 2 from here that I can pull out because that's a constant. Then I have a new integral. Limits are 1 and 4. Yes, and then what do I have? I have 1 over square root of u here, and then I have du. And this is extremely simple integral. So first of all, this 3 and that 3 are cancelled, so I will have 1 over 2. An integral of 1 over square root of u when u itself is variable is just 2 square root of u, and then I have to run it from 1 to 4. Yes? So what will happen? So this becomes, this 2 and that 2 are cancelled. This becomes a square root of 4 minus a square root of 1. It becomes 2 minus 1. And the answer is 1. Okay? So the answer to this integral is 1. I hope that this video was useful for you. So until the next video, be safe and goodbye. Thank you.